This unit is going to actually discuss kinetics, and the first slide that you have here is probably going to look a little familiar because we actually talked about kinetics a little bit in the beginning of our thermodynamics unit. What you need to remember is this measure of the speed of any change that occurs within an interval of time is called a rate. Now, in chemistry, we usually express the rate as the amount of reactant that is changing per unit time, or sometimes we even can refer to it as the amount of products that's being formed per unit time. The thing you need to remember for all the way back from our thermodynamics unit is before reactants can change into products, they first have to collide into each other with enough kinetic energy in order for that reactant to change into products. This is known as collision theory. And the minimum amount of energy that colliding particles have to have in order to react, we refer to it as the activation energy. So from our thermodynamics, we used to have a picture that would show this activation energy hill. So you'd have a certain amount of energy here, and your reactants would start here. You have to add a little bit of activation energy. As soon as that activated complex is formed right up at the top here, you would get a release of energy. So here we're breaking bonds in order to create the activated complex, and this part here we're actually forming bonds. And if we receive more energy from that reaction than we had to actually put into it, then we actually call that an exothermic reaction because energy is going to be released. And then an endothermic reaction would look like this, where we actually start with a big activation energy hill, and then we end up with some products here. So we have bonds being broken, new bonds being formed. But the important thing here is this, that all has to do with collision theory. These particles need to collide into each other in order for those new substances to be formed. And that high energy state that has to be formed is called the activated complex. This should be a review from our thermodynamics unit. But the thing you want to remember here is that particles need to collide into each other in order to create a new product. So reactants have to collide into each other with the right amount of energy, and they also need to have the correct orientation. And we'll talk about that a little bit later on in the unit. So the particles need to collide with enough energy, and they have to be turned in just the right way and have the right orientation in order to create this activated complex, which would then change into products. So if we look at a pair of reactants here, and we have these diatomic blue and diatomic red elements kind of moving all around randomly inside the container, probably a gas. And what we notice when a reaction is going on is that as time continues, the reaction or the rate of reaction actually slows down. And the reason that this is happening is because the number of available reactants is decreasing. So when these particles collide into each other, they form these new products, and these new products are now going to be in the way. These guys are going to be now moving around inside of the container, and it becomes a little bit more difficult for A and B here, or the red and the blue substances, to actually find each other inside the container. So the number of available reactants that inside the container is going to go down, and the newly formed products are going to make it difficult for the remaining reactants to find each other to create this new product. Other than time, there are 5 other factors that will affect the rate of reaction. And what you want to think about in every single one is this idea of collision theory, the idea that reactant particles have to find each other inside of the container, have a collision with the right orientation, and with the right amount of energy. So these guys here probably would not actually form a product because they're kind of hitting off center. They may be hitting with the right amount of energy, but no reaction is actually going to occur. And then this one right here is not going to form any products because you have 2 of the same reactant actually colliding into each other. Now, sometimes that might create a side reaction, but for this reaction, we needed the red and the blue to actually slam into each other with the right orientation and the right amount of energy in order to form products. And if it doesn't, then you're not going to get any products formed. As products are being formed, though, the reaction will slow down as time goes on. So there are 5 other factors that we need to take into consideration other than time that causes a slowdown in a chemical reaction, and these are going to vary. One of them is the very nature of the reactants. If you look at these two chemical reactions here, and I ask you which one do you actually think is going to occur faster at room temperature, what you have to think about is that in order for a chemical reaction to occur, these particles need to collide into each other, and they have to have the right amount of orientation, they have to have the right amount of energy and the proper orientation in order for that to occur. That's all about bonds being broken. So when you're looking at these two reactions, we actually need to have bonds broken. We need to have bonds broken between the hydrogens here. We need a bond between the oxygen to be broken to reform into the water molecule here. And on the other one, we need a bond to be broken between the sodium and the hydroxide ion because we're actually adding water. So we put water over the arrow here, and it's going to make these two aqueous ions. The one that would actually occur faster is this one right here. And the reason is because the sodium and the hydroxide ions are the sodium and hydroxide ions are held together by ionic bonds. Ionic bonds are weaker than covalent bonds. So the covalent bonds in the hydrogen and the oxygen they need to be broken are much more difficult to break apart than the hydroxide ions. I'm sorry, than the ionic compounds and sodium hydroxide here. So the one that is occurring faster is because you're only breaking ionic bonds. And I would actually write that somewhere in the margin of your flip lesson notes. The reaction on the bottom here is even faster. Okay, the fastest reactions that can occur are when the number of bonds that you need to break is 0. So we have 0 bonds to be broken in this because if you look carefully, we have these little aqueous symbols right down here. Now these aqueous symbols mean that these substances are already mixed in water, so the bonds between the silver and the nitrate and the sodium and the chloride ions are already broken apart. These are free floating ions moving around in the solution, and it forms into this solid silver chloride substance that's going to precipitate out, and then these sodium and nitrate ions are just going to be freely floating around. So if between the 3 of these reactions, the bottom one would actually be even faster because there are actually no bonds that actually need to be broken there. The top one's the slowest because we're breaking covalent bonds. The middle one is faster because we're only breaking ionic bonds. And the bottom one is the fastest because we are not breaking any bonds whatsoever because they're already broken from being in an aqueous solution. So the ionic bonds are already broken in the reactants since the ionic compounds in water are already dissociated or broken apart. The second factor that affects the reaction rate are changes in concentration. And if you look underneath where I wrote changes in concentration, I have the little red plus symbol plus the little triangle yields a little smiley face. And the smiley face is going to be our product in this reaction. So we have a control container where I just kind of randomly place some particles there. And then I have the middle one where I've actually added a bunch of plus symbols, and the last one I've actually added a bunch of smiley faces, but it's essentially the same picture. And the idea here is to show the second picture where I added a reactant, which is the plus symbol, and in the end one there, we're adding a product. And what we got to think about here is how would this affect the rate of reaction when a higher concentration of a reactant is added. So we're looking at the middle picture here. Uh, the if we actually add more of those little plus signs in there, the reaction is actually going to occur faster. And the reason for that is because the reactant particles can find each other a lot easier to have a collision. If you look at the control, the triangle and the plus sign here have to actually slam into each other with the right amount of orientation and the right orientation and the right amount of energy in order to create a reactant. If you add more reactants, what's going to actually happen here is that these triangles are going to have a lot easier time finding one of these little plus symbols inside the container in order to have a chemical reaction. So you don't have to add both reactants in order to make the reaction go faster. Just the addition of one reactant would make that chemical reaction occur faster. If you added more products, though, if I just added a whole bunch more of those little smiley faces in there, the reaction is actually going to occur slower. And the reason is again, the idea behind collision theory. The reactant particles are going to have a more difficult time finding each other inside the container. So here's this plus symbol. It's got to find this triangle here, but you have these other smiley face particles here, these products that are getting into the way. When that happens, this reaction is going to occur a lot slower than our control, where we only had a few of those little smiley faces that they would bump into and cause problems between the two reactants. So if you add a reactant, the reactant particles find each other a lot easier in order to collide. If you add any other substance, a product, or even if something was something inert like a noble gas inside of this container, any particle that you add that's not actually part of the reactants and it's hindering the reactants' ability to find each other to create a reaction will actually cause the reaction to slow down. The third thing that affects a chemical reaction is temperature. And what you got to remember is that when I increase the temperature of a reaction, it's the same thing as increasing the average kinetic energy of the system. So you're actually adding more energy to the molecules. They're going to move a lot faster, and increasing the temperature of that system will therefore increase the rate of a reaction every time, because for two reasons. First of all, the particle collisions are going to happen with more energy. So you're going to get more particle collisions that occur with a high amount of energy, and the more energy you have, the easier it is for those particles to actually undergo a chemical reaction. Also, increasing the temperature will increase the frequency of collisions. These collisions are going to happen a lot more frequently and with a lot more energy, and that just makes common sense that this chemical reaction would actually occur faster if you increase the temperature, and a chemical reaction will always occur slower if you decrease the temperature. The fourth thing that affects a chemical reaction is surface area. I have a little cube of sugar here that's tied to a string in the lower left-hand picture. And those, actually, I'm sorry, that's a block of salt. So we have sodium chloride, and we got sodium ions and chloride ions that are being solvated by the water molecules. And you can see the red oxygen ends of the water molecules are facing in towards the positive ion like they should be, and the hydrogen ends are facing in towards the negative ions. And if you had a big block of sodium chloride, you got to remember that only the salt on the outside edge of this piece of salt is actually going to be able to be solvated with the solution. The water molecules have to have contact with that salt in order for that to occur. If I wanted this salt chunk to dissolve more quickly, I could just break it apart into smaller pieces like I did in the picture above. If I cut it into more pieces, what happens now is that the solvent has more contact with the solute, and it'll cause it to dissolve a lot faster. So the thing we have to remember here is that increasing the surface area of a reactant provides greater contact between the reactants and more opportunity for a chemical collision to occur. Therefore, increasing the surface area of the reactants in a chemical reaction is always going to increase the rate of reaction. If you have a very small amount of surface area, like a big old block of something, like a big chunk of zinc that you're putting into hydrochloric acid, that'll occur a lot slower than if you ground that piece of zinc into a fine powder and pour it into the hydrochloric acid right away, because you'd actually have a chemical reaction happen right away, as the zinc has more contact with the hydrochloric acid, just like this piece of salt would have more contact if I ground it up into little bits and threw it into the water rather than just having this big block suspended by a little string there. The last thing to talk about that affects the rate of reaction is the addition of a catalyst, or also something called an inhibitor. By definition, catalysts bring about a change in the reaction mechanism of a chemical reaction. Enzymes are one example of a catalyst that you probably talked about in a living environment, and there's a picture of it on the upper right-hand corner. What happens here is you got two substances, the purple and the like the orangish yellow particle here, and you have a catalyst that has a molecular structure very similar to your reactants and allows them to actually get locked in place onto the catalyst. These reactants actually will stick to the catalyst, and therefore it puts them in the right orientation so that when the catalyst releases reactants that are actually can bond together very easily because the catalyst kind of forces them to turn in just such a way so that it's a lot easier for a chemical reaction to occur. So it basically creates a new reaction pathway that lowers the amount of energy necessary for a collision between the reactants to form a product. In a sense, it causes a decrease in the activation energy, and that's what's being represented by this red curve right here. The blue curve represents a normal reaction pathway without the catalyst, but if you have the particles already bent in such a way so they're a lot easier to have a chemical reaction, you need a lot less energy. So by lowering the amount of energy necessary for a collision to occur and decreasing that activation energy, you're going to increase the rate of reaction. It's just going to happen a lot faster. And with a lot of companies, the faster you can make a product, the better. Now, sometimes chemical reactions can happen so quickly that they can start to become dangerous. That might be where you actually have to add an inhibitor, and an inhibitor is something that does the exact opposite of a catalyst. It slows down the chemical reaction, and it'll create a larger activation energy, and therefore slow down the actual rate of reaction because you need a lot more energy per collision in order to create a product. And that ends our discussion on kinetics and the 5 major factors that affect a chemical reaction rate.